All right, so today we're going to keep talking about force. Remember, Sir Isaac Newton was around, I think, what was it, 1647 is actually when he was born. And Galileo said if the net force is equal to 0, then there's no acceleration. So that was before Isaac Newton. So the interesting thing about that is you could have 5 newtons of force going this way and 5 newtons of force going in the negative direction. They cancel each other out mathematically, and so you have 0 newtons. Okay? So net means what they add up to. So you have a positive direction. Remember we said yesterday that forces were vectors, so they have a direction. And generally what we do is we keep the forces linear. Sometimes we'll do an x direction, and then we'll do the y direction separately. And so then you have a positive or negative direction, right? For y, going up is positive, going down is negative, and then for x, usually going to the right is positive, and going to the left is negative. And you know, if you take physics in college, you'll do a z direction, which positive, that one's a little trickier. Positive could be coming towards you or moving away from you, and then the opposite would be negative. In three-dimensional calculations, they tend to pick whatever is the most convenient. There's a lot of rotations of axis and stuff like that. So anyways, if the net force is non-zero, then the number will be an acceleration. So if I have 5 newtons going in the negative direction, I have a negative 5 newtons. And if I have 2 newtons of force going in the positive direction, then my net force is going to be negative 3 newtons. And that's just negative 5 plus 2. So it accelerates, but it accelerates in the negative direction. So that's going to be a little confusing for some people. Usually they associate negative acceleration with deceleration, but that's not always the case. Acceleration just really means, we're used to saying accelerating, like a car has an accelerator, the gas pedal is referred to as the accelerator. But it's a change in speed, right? That's what you guys are used to hearing. In most cases, the car speeds up when you hit the gas, so they call it the accelerator. But technically, the brakes are accelerators too, because it slows you down. They decelerate the motion of the car. Also, because velocity is a vector, the steering wheel is an accelerator. In other words, it changes the direction of the velocity. So there's that. Does everybody have this written down? Okay. Moving on. Going once, going twice. All right. So after Sir Isaac Newton, force is the cause of a change in speed or direction. So we're kind of doing the history of this. Remember I said Sir Isaac Newton didn't invent all this stuff. He built upon other things, right? I said that he built on Galileo's work, and actually Aristotle, he had some ideas too. And there were other people. Galileo took more of a scientific approach. At some point, philosophy and science kind of deviated, right? So philosophers just love to think about stuff. They just sit around and think about stuff. And so they would think of things like, why do I exist? How do I know that I exist? What are the fundamental elements? What is everything made up of? So they're just thinking questions and thinking. And so they're going, well, I think everything's made up of I don't know, fire, water, earth, air, right? And then that expands, right? A more scientific approach is, what are things made up of? How do I prove that they're made up of these things? How do I verify that these things are made up of these things? So they expand on, in a scientific method approach, and through the centuries, people like Galileo really honed in on measuring things, making calculations, and Isaac Newton just kind of built on that. But he built on it in a profound way, such that we still use his equations today. So, force is usually represented by the symbol F. It can be measured with a spring, right? It can be measured with a spring. When we met last time, I weighed one of my masses with the spring. And the unit of measure is newtons, and 1 newton is equal to 1 kilogram changing its speed 1 meter per second per second. Did I weigh the thing with the scale with you guys to show you the difference between weight? While you're writing that down, I'll do it right now. So while you guys are writing this down, I'm going to grab a scale. Remember that weight is the measurement of the force that Earth applies on an object. The object applies the same amount of force on Earth, just that Earth doesn't move. So the acceleration due to gravity is 9.8 meters per second. So I have 1 kilogram. This is a mass of 1 kilogram. It doesn't weigh 1 kilogram. It's a mass of 1 kilogram. This scale tells me the weight. So the mass is 1 kilogram. And remember, force is mass times acceleration. So the acceleration when I lift this off the ground is going to be 9.8 meters per second squared. So it's going to be 1 times 9.8. When I lift this up, look at the scale. Where does it look to be? So the weight of this is actually 9.8 newtons, but the mass of this is 1,000 kilograms. Or not 1,000 kilograms, 1,000 grams or 1 kilogram. Okay? Put it in the video. Woo! Okay? If that scale wasn't holding that mass, as soon as I let go, it would speed up at 9.8 meters per second. Anyways, we measure that force in newtons. Does everybody have that written down? So what we do then is we add up the vectors. Okay? What do you guys think this first one will be? Well, we did that on the other problem, right? It was -3, right? What do you guys think this, you don't have to write this down, but what do you think this would add up to? The vectors in the red. Well, you just add them up. What's 7 plus 3? What's 10 plus 5? 15. Then you subtract 3 from 15, what's that? 12. So the net force of these is 12. Does that make sense? Now, technically, these are the answers. It's not a separate problem. These are the answers to this one. So what's the answer? Yeah, B is -3n. I just did that extra stuff just to kind of keep you guys on your toes. So write this down. The normal force is the force that pushes perpendicular to the surface of an object So my remote for my projector, when I set it on the countertop, Earth is still pulling down on it. The reason it's not falling is because my bench is pushing up on it. And they're equal. So if Earth is pulling down on it at 9.8 meters per second, the bench is pushing up. And if we were to calculate the force, it would be the mass of my remote, the mass of this bad boy right here, times 9.8, actually a negative 9.8, because going down towards the center of the Earth, we usually, going down in the y direction is negative. And then whatever that number is, the positive amount of force is being applied in the opposite direction. That's what keeps the remote still. All right, so you need to, I want you to write this. I want you to write this out. So really what's going on is if you have the force of gravity pulling down on something, the normal force is pushing up. Equal in magnitude. Notice those two arrows are the same length. I don't know why there's a fish over here and a bobber, other than maybe the bobber is being pulled down towards the center of the Earth, but the water is pushing up. So it just kind of rests on the surface of the water is one way to think about it. If that water wasn't there, that bobber would fall down for sure. But this is really more buoyancy, which, I don't know, there's a force, there's a buoyancy force. Okay. I see a couple people still writing it down, so we'll wait till you're done. Okay. Can I go now? Okay. So write this down. Friction opposes motion when an object touches something. And we'll just write that down. And so when you're done writing this down, I want you to take your hands and put it on your desktop there and push forward. When you do that, what do you feel? The desktop is pushing back against you. Now try pulling your hands towards yourself. You'll feel the desktop going in the opposite direction of the motion. That's friction. Friction on a microscopic scale, your hand, believe it or not, has rough surfaces. That seems to make sense because we have fingerprints and stuff like that. But the smooth surface of this desktop has, if you looked at it under like an electron microscope, you would see that it's not perfectly smooth. It has little ridges. And so those ridges kind of lock together, right? So my hand on top of the desktop, and they kind of lock together. Now, if you push hard enough, you can overcome that. That's what friction is. That's what friction is. So whenever you rub two things together, you're kind of overcoming those molecular, when a molecule isn't perfectly smooth. It feels smooth to us because we're bigger than a molecule. But the molecules, sometimes parts of them stick up a little bit. So it kind of looks more like this. So there's different types of friction. Static friction means the object is static. Static means stay. You can think of it as the word stay. But static means that it's not moving. So static friction, opposing motion of one solid object, not sliding against one another, stationary, right? Those all have the same root word. So this is the greatest friction for an object because it wants to stay still. Those grooves are locked in pretty tight. Once you get something moving, you kind of bounce off the grooves. But static friction is definitely one type of friction. So that's the force opposing the motion of one solid object, not sliding against each other. Keeps the object stationary. So if I take this remote and I put it on a ramp, it'll stay on the ramp as long as the ramp isn't too steep. What holds it in place is static friction. Also, at some point, we'll talk about the different types of static friction. So some things have more friction than others. Aluminum, because it tends to hit the molecules are closer together, that has less static friction than, say, a rubber tire. Because the molecules of the rubber grip more, and that has a lot more to do with the molecules than anything else. So if I were to try to rub two rubber tires together, the static friction would be a lot greater than if I were to try to rub two pieces of aluminum together. It'd be easier. Okay. All right. Another kind of friction, by the way, this is the strongest friction. I'm going to skip past this stuff. Another kind of friction is like a sliding friction. So if you slam on the brakes on a car, you'll get static friction. And then you can have sliding friction. Anti-lock brakes kind of focus on, they turn on and off so the wheels don't slide. Because the static friction is the strongest. Okay, you don't have to write this down necessarily. This is just an example to think about. Okay. And you'll see this in your car's ABS or a car sliding. Now, kinetic friction, that's sliding friction. That's a force opposing one solid object sliding over another. So it's technically called kinetic friction. Sometimes it's referred to as sliding. So if you take your hands, when you're done writing down the stuff, take your hands and rub them together. And you'll feel the friction between them, but also your hands will get warm. So kinetic or sliding friction is the second greatest friction. So static is always the highest. Next is sliding or kinetic. Okay. Can I move on to the next slide? Okay. Rub your hands like this, you guys. Do you feel how they get warm? That's because of the friction. We put a lot of energy into rubbing our hands together, and then to overcome the friction, some of that energy gets turned into heat. That's a different lesson, but the next one is called rolling friction. And just think of like a wheel on a car. So this force acting on part of a wheel that travels on a flat surface. So there's a little friction between the tire and the surface where they make contact. But because the wheel is rolling, rolling friction is very minimal, right? But it still exists. So I'm working, and we'll do this towards the end of the semester, but right now I'm currently working on a roller coaster project, similar to the T-shirt project. But the roller coaster project, we have to consider the energy and where does the energy get used up. So the energy starts at the first big hill, and it's called potential energy, and then the roller coaster basically falls down the rest of the ride. But some of the energy gets used up, and most of it gets used up in friction. So there's some sliding friction, there's some rotational friction. Sometimes the carts bump into each other. There's some friction in the beginning. So there's static friction. And if you take all that friction, that frictional force, and subtract it from the energy that you have in the beginning, you'll see that all the energy is conserved. I'm really oversimplifying it, but that's the case. Those are things that engineers that make roller coasters have to think about. Okay. Can I move on? By the way, this is also how police officers tell, like, when they say when somebody's in a car accident, they'll say they were doing, 80 miles an hour. This is how they know. They know what the frictional force is between a rubber tire and concrete. And so if somebody locks up their wheels and the tires slide, they could figure out based on the skid marks how fast the car was going when they locked up their wheels. And that's physics. I mean, they don't sit down and do it with a piece of paper. Somebody like myself makes a computer program, and they enter in how long the skid marks are and what type of car it is, and then it figures out the weight of the car. And then if it, the normal force times the coefficient. Anyways, let's move on to the next one. One of my professors in college, a physics professor, he actually would get called in from time to time to court cases, and he'd have to explain the validity of the police's assessment of how fast the car was going. He'd have to explain the physics. Number 4 is fluid friction. Now remember, air or a liquid is a fluid, right? At least in a physics perspective. Now there's a difference between gas and liquid, right? And you learn that in middle school, like what's a gas? You learn the states of matter. What's a gas? What's a liquid? Right? What's a solid? But fluid is referring to gas and liquid. So everybody thinks fluid, oh, water's a fluid. Oh, oil's a fluid. Well, air is a fluid too, and from a physics perspective. So this is something that we deal with the T-shirt launcher. It's going to have air friction, which is technically fluid friction. It's going to have to move air molecules out of the way. So it's going to resist the motion. So even though we can calculate where that T-shirt's going to land, it might not make it that far because of air friction. But if it only falls a foot short, we don't care. They just got to reach out with their arms to catch it, right? Now, something that goes really fast, like a jet, they're going to run into a lot more fluid. And remember I said yesterday I like to stick my hand out of the car window. Can I move on to the next slide? How many of you guys drew a picture of the dog? All right, so these are the 4 types of friction, at least that we're going to cover in this class. And so the greatest one is static. The next one is sliding. And you should write this down. It's literally on your homework. And also going to be on the test, so you'll want this in your notes. Then rolling, then fluid. And this really, if you think about it, it has a lot to do with how much contact between the two objects. Static, those grooves between the molecules of the two objects almost interlock. When it's sliding, they're closer to the surface because it's already in motion. You've already pulled it out of the grooves and you're moving. Rolling, it's just minimal. You've got this kind of thing going on. And then air friction or fluid friction, there just aren't that many molecules. They're spread out. So because they're spread out, it's the least amount of friction. Now, friction, I don't know if we pointed this out, but friction is a force. That's why we're mentioning it in forces. Does that make sense? That's why we're talking about it in our force section. Does everybody have this written down? All right. So gravity is a force of attraction between any two objects. Towards the center of the objects, always on Earth, the acceleration is 9.8 meters per second squared. Some people will just use 10 because the math's easier. You got to multiply by 10, divide by 10. It's a little easier, but I'll always use 9.8. You'll definitely want to write these down in your notes because they'll be on the test. And so when we talk about gravity, the Earth pulls on the moon and it pulls on each and every one of you. And the acceleration that it pulls on everything is 9.8 meters per second. While on the surface of the Earth, it doesn't pull on the moon. It doesn't accelerate the moon at 9.8 meters per second because the moon is a lot farther away from the surface of the Earth. So that number is smaller. But it's pulling on the moon just like it's pulling on us. The moon is in orbit because it has a motion. It's technically pulling away from the Earth with the same force that the Earth is pulling towards it, so it remains in orbit. Anybody ever been to the ocean and seen high tide, low tide? So a great example of high tide, low tide, and gravity, wherever the moon is with respect to the Earth, it pulls all the water of the Earth towards it. So the moon does have a gravitational pull. So if the moon is over here, the majority of the water over here gets pulled towards this side of the Earth, not the majority, enough that it's noticeable. And so it would be low tide over here. If we were to move the moon over here, then it'd be high tide over here and low tide over here. And that's just because the moon has a gravitational pull. Can I move on to the next slide? Okay. This is all the people on Earth, I guess. You don't have to write that down. I'm not doing that. I think we're almost done. Okay, write this one down. So if you jump out of an airplane, you will accelerate towards the center of the Earth at 9.8 meters per second. But remember that thing we talked about, fluid friction? You're going to be falling through a fluid, which is air. So at some point, the air friction is going to stop you from increasing your speed. Earth will still be pulling you down. You'll go pretty fast, but at some point, the air molecules, you're going to hit so many, they're just in the way, and you can only fall at a certain speed. A great example of terminal velocity is take a big heavy rock and throw it in water. It hits the water really fast, and then it just slows down and falls at a steady rate. That's terminal velocity. Well, water is a thicker fluid than air, but your body will do the same thing if you parachute out of a plane. And what a parachute actually does is it gathers more air molecules, so that makes your terminal velocity even slower. That's how they work. So you basically fall down at a slow speed. Now, if you didn't have a parachute, it would look a lot like this. So actually, the terminal velocity for a person without a parachute is about 120 miles per hour. You'll never go any faster than that. Why? Because the air molecules are going to push up and gravity is going to push down, and you'll kind of lock in at the speed of 120 miles an hour or 60 meters per second. What is that? Does everybody have this written down? All right, let's go on to the next one. So projectile motion, both forward speed and downward acceleration. So our T-shirt launcher is actually a projectile launcher, where the projectile is the T-shirt. So we're going to have a forward speed and a downward acceleration, eventually moving down very fast. Hey, what does this remind you guys of? Didn't we shoot a dart off the edge of your desktops, the tabletops? Well, this is the path that it would travel. I think my colleague's having a little fun. I don't know why you wrote that. But basically, once it leaves the launcher, whatever it is, the projectile is going to be pulled down towards the center of the Earth, and it's going to speed up and speed up and speed up and go faster and faster and faster. Sir Isaac Newton actually made up equations that could calculate how fast it'll be going at an instant in time. And those are the same equations that we use today for NASA and SpaceX and all that stuff. You don't have to write this down. And that's it. Any questions? All right. So give me 2 seconds and I will post your homework.